Hello. So my name is Joel Lehman, and I'll be giving a talk today on this paper, Evolution Through Large Models, which was done with this list of fine co-authors below, and this work was done at OpenAI. So the main motivation for this work involves evolutionary algorithms and large models. And the hope here is to bring these two together in a way that has a lot of synergy, so that there's something that an evolutionary algorithm could bring to large models, and there's something that large models could offer to make a new kind of evolutionary algorithm. And so the main idea of our paper is an approach called evolution through large models. And one of the key insights is that language models that are prompted or trained to generate changes could be a powerful operator for search. For example, if we imagine, so we'll be dealing with examples in the code domain here, trying to work with program generation. If we look at GitHub, for example, you can imagine training on a scrape of GitHub to create a model that could autocomplete code. Or you can imagine also looking at diffs on GitHub. So on GitHub, if you it's not only an archive of a particular version of a piece of code, but also a revision history for all the little changes that happened. And so we can actually train a language model to know how to make changes. And if we had this model that was able to make coupled intelligent changes to code, then perhaps we could use that to create an evolutionary algorithm with a variation operator, like a mutation operator, that could actually make meaningful coupled changes to code as well. And this is the basic idea behind language models helping evolution in this approach called ELM. But we also go the other way around and show that evolutionary algorithms can help large models. And so one idea here is that there are a particular kind of evolutionary algorithm called a quality diversity algorithm, or QD, that searches for diverse, high-quality data examples. And the idea is that if you had a domain where there's little training data for that particular domain, so maybe a new programming task, then could you use this algorithm to start out with a single seed example and diversify from that single example and create a large diversity of high quality different kinds of examples to create an effective training set that could then be used to fine-tune the language model into competence in this new domain. So this is the other direction where evolution could help language models. So for the rest of the talk, I'll be kind of going into some detail about kind of this three-stage approach that we used in this paper as a proof of concept, where first we'll use a QD algorithm that is using a language model as its engine of change for the evolutionary algorithm to take a single data point and diversify it onto a data set. And then we'll use that to fine-tune a language model into competence in that new domain. And then we'll take it even a step further and to show how this knowledge could be used for some kind of downstream kind of thing by then training this model further with reinforcement learning to transfer this learned ability into another context. So I'll dive into each of those components in more detail as we go forward. But first, let's take a little bit of a step back and look at a little bit of background behind these things so we get a better sense of what this approach is really about. So I'll talk first just a little bit about language models, and in particular about these kinds of code-generating models that will be used in this work, and also kind of give a little bit of an intro to evolutionary algorithms. So at this conference, probably there's not a lot of need to go into an incredible amount of detail into language models. So probably many of us are familiar with these things. Increasingly large machine learning models, billions per parameter sometimes, trained on natural language. And they're important because they've really enabled a lot of rapid progress in natural language understanding and generation. Like pretty profound progress relative to where we were, say, like a decade ago. And for the purpose of this talk, I'm going to focus a lot on the rapid progress in models that can code, for example, like OpenAI's Codex, all those other kinds of coding models out there. And so far, the recipe for improved performance at a high level for these kinds of models is bigger networks, more data, more compute. But for some domains, you might not have a lot of data. And so, for example, for a new programming task. And so the question, an interesting question is, can you actually use large models to create new data for themselves? So you actually have an engine of data creation. That's kind of one of the things that this paper focuses on. So let's talk a little bit about code generating models. So these are models that are often trained in kind of like a next token prediction kind of way, like the way that you would train a GPT style model. You train them on, for example, like a scrape of GitHub. And a lot of the popular applications of these things so far have been kind of in the intelligent autocomplete kind of way. If you've seen or played around with the Copilot plugin, basically it will attempt to continue your program as you suggest a new line for you to insert, for example. So your way of interacting with this is providing some kind of prefix, like the program so far, maybe a definition of a function, and the language model will then try to offer a completion of that to try to help you automatically generate something. So for example, if you had this bit of code that's defining a sum of square roots function, and you have some description of what that function is, something like Codex could autocomplete the rest and try to predict what will actually be a correct sum of square roots kind of function. So that's kind of the coding model side. And what about evolutionary algorithms? So remember, we want to kind of bring those two things together. So evolutionary algorithms are really simple black box optimization algorithms. They're kind of trial and error search algorithms inspired by biological evolution. So the typical evolutionary algorithm loop is to take some sort of initial candidate solution and create a lot of variation around it, either by randomly changing bits of it, or crossing over solutions, trying to mate two solutions together in a way to create another generation that would have some distribution of solutions in it, and you have some metric you use to kind of call that down. So you keep kind of generating diversity and selecting the best of those to kind of be the seeds of the next generation. So although these algorithms can trivially benefit from increased computation because they're very parallelizable, they don't benefit from data or large networks in the same way that language models do. So a question we ask in this work is, can language models instantiate intelligent mutations for an evolutionary algorithm? So one way of thinking of this is kind of going beyond the paradigm of just random mutations, like in DNA, for example, and in actual biological organisms, mutations happen randomly. If we think about like humans actually riffing in the space of ideas, for example, there's actually directed change. There's intelligent change to an idea. It's not completely random. And if two people are brainstorming together, they're operating at this kind of more semantic level. And that's kind of the motivation for wanting to have an intelligent mutation operator. And so once again, the hope here from the side of like, so one hope is that the evolutionary algorithm can benefit from the intelligent mutation provided by language model. And the other side, we want to leverage evolutionary algorithms to create new data for language models. Okay, so that kind of sets the stage for the kind of main approach of this paper. And so I'll focus most on this first stage, which is about how we can use this technique to generate an initial data set from kind of bootstrapping from a single example outwards to create more data. And then the other two stages are more or less kind of demonstrations to show how that data that we generate could be of use in downstream kind of applications. So the domain that I'm going to be highlighting is kind of like a little bit obscure, and it's about it's called Soda Race. And in Soda Race, the idea is you can have a Python program that could describe an ambulating robot. We chose this domain more or less because we have previous experience in it, and because it's kind of visually interesting and kind of a simple proof of concept. So we have Python programs that will translate into these soda racers, and these robots will have, they're kind of open loop control. There's no neural network that's controlling them, but they're just kind of mechanical robots that kind of move on their own. And so we try to create, so this is one other reason for this domain, is that it's a domain that there's not a lot of training examples for, because we kind of invented this particular variant of it for this paper. And the basic approach that we're going to be applying is kind of demonstrated by this slide. So we'll be using a particular evolutionary algorithm called MapElites, which is a quality diversity algorithm. And its main objective is to to fill out a space of different niches and keep trying to find the highest quality solutions in each of the niches. So in this diagram, we have this map of diverse champions, and we have some predefined measures of diversity that we're interested in. So in this case, let's say we want to find a lot of different ambulating robots that vary in their widths and their heights. And we could create this kind of 2D grid. In the paper, it's actually a kind of a 3D cube of little grid squares. But here, let's just look at a 2D grid. And so what we want to do is imagine we have an initial Python program that defines a very simple soda racer robot. If we evaluate that program, it will generate the robot, and we can figure out where in this map it goes. What's the width of this robot? What's the height? And it goes into this map. And then we'll just have this loop of taking the Python program, randomly choosing one of these. Well, to begin with, we'll take the grid square that robot landed up, because we only have one. We'll take that Python program, we'll run it through a diff model, a model that's actually going to generate intelligently a change, propose a change to that program, get the resulting program out, evaluate that program, and if it's a correct program and it results in generating a soda racer, then we look again to where in this map it could go into. And if it's a grid square that hasn't been filled yet, it'll actually colonize that grid square and fill in that niche. And if it maps into a niche that's already filled, so there's already been some soda racer with a similar height and width, we'll check and see if this new soda racer outperforms the old one. So in this case, we're looking for soda racers that can navigate further. So if the new robot navigates forward better, for locomotes faster, then it displaces the old one. And so this loop just goes on and on and on, trying to fill out this grid as much as possible with as many good examples of soda racers of different widths and heights that can locomote quickly. So the basic idea is that this diff model here is the thing that's going to be where the language model fits in. It's taking just plain text Python programs and just changing them in some way. And through iterating, the hope is that we take this one initial example and sort of diversify it out, create all these different training examples that we can use later to fine-tune a model. So let's talk a little bit about that diff model, just to kind of give us a sense of what that really looks like. So we had this slide earlier about a coding model that was able to autocomplete. And this is kind of the typical code generation kind of language model approach. Now, once again, you take this the sum of square roots, you fill it out. But now if we want to think about what would a diff language model look like. So if we actually trained a language model on a file, the commit message describing the change to that file, and we try to predict from that the diff. So like we have these tuples of that from say a scrape of GitHub on like a file, a commit message, and the change that we're committing to that repo. This would be one way to train a model such that we would suggest changes after we train it. So in fact, this is just a way to learn the distribution of changes from like the history of changes on GitHub, and then predict for a new Python program or function that we want to change, a way to kind of get diffs out of that will help us to suggest new changes that could be useful to us. So for example, this is a simple function from our paper, just like a parity testing function. Like it's a bit parity function. It's not really important to understand exactly what's going on beyond that. There's a typo here, that all of these variable names, these C1 through C4 in this red circle, they don't match with the function header. It should be B1, B2, B3, B4. And if we had this commit message, a fixed bug, along with this program that we fed into this diff language model, then one thing we would find, if we trained it well, likely, is that it would do this. This is actually one of the samples. Is that it would actually change the C's into B's. So all those kind of correlated changes, it can do that in one step. And what we show is that if you were to use like a regular evolutionary algorithm, now a regular evolutionary algorithm that is just making random changes, which would be how you would ordinarily do this kind of thing if you're using an evolutionary algorithm to evolve code, then as you might expect, with the number of bugs, here the line that says GP mutation, the success rate goes down really, really quickly. This is actually it's a logarithmic plot, so it's really getting a lot worse as you have more bugs, which makes sense. whilst the diff-based mutation is able to kind of make, in one step of mutation, correlated changes with these number of bugs, and it can still actually be efficient. So this is kind of highlighting that there's a qualitative difference between a random mutation and an intelligent mutation, which makes sense. So again, the domain that we're going to be doing this in is this kind of ambulating robot kind of domain. And these robots consist of point masses and springs that connect those point masses. And they'll be kind of locomoting on some terrain. And so in the beginning, this terrain will be flat, but later, when we get to the reinforcement learning, the terrains will change to be different kinds of terrains, like bumpy terrains, for example. And so the way that we have this domain is that we create like a Python-based interface into creating pseudo erasers. So this is just a chunk of code that's the listing for one of the seed programs that could start off our evolutionary search. And it's a program that describes this kind of simple square. This is the square seed at the bottom of this animation. So there's different seeds here. So we explored in the paper, like what would happen if we started with one of these different seeds, whether it's these barely functional kind of robots that more or less just sit in place, and how a search that starts with one of these things and tries to diversify that into a whole training set, like what's the influence of that? And it turns out that there is an influence. But for now, just the important thing is that this program on the left is one way that you could describe this square pseudo eraser on the right. Like it constructs that pseudo eraser by programmatically defining, like, let's add joints, let's add muscles that connect those joints together. Okay, and now we're returning again to this plot. So hopefully we're returning this with a little bit more context. That the diff model that we maybe now understand is kind of the key to this evolutionary algorithm. It's a very simple evolutionary algorithm. Once again, we're just kind of going to keep trying to pick solutions that are in our map, try to elaborate upon them with the diff model, and see if they either discover a new yet unfilled square in this map, or that they improve upon the thing that we discovered before. And as we keep running this longer and longer, the idea is that we're going to fill out this map and have a data set of good examples of these programs that represent these pseudo erasers. And in fact, as we run this algorithm over time, we get one of these nice plots where performance increases over time, as you would expect. The y-axis here is just some measure of how the robots are doing. And there's also a way where there's this green line, which is if we use a pre-trained diff model, just train the way that I said. But if you fine-tune the diff model as you go, so actually, the diff model has never seen these kinds of pseudo eraser examples before either, and so we actually can fine-tune the diff model and actually accelerate search as we go by giving it more examples of successful diffs that improve performance or colonize a new niche. Okay, what we end up with is lots of cool creatures that are invented through the system that really are quite different than the original seed. And so in this case, there's a way that we've created a really cool data set. So let me go. Oops. Okay, so basically that's kind of showing that you can create a data set. And these two other stages are showing that you can fine-tune a language model and do RL on it. So for the purpose of time, I'll just highlight this one result, which is that basically, as we increase the model size of the language model that we're taking and fine-tuning from the data set that we created, we get more and more generalization and kind of better performance. And the third step is, like, can we actually do reinforcement learning on this? Can we actually make a model that now reacts to the different terrains that we give to it, so like the bumpy terrain or the tunnel terrain? And so now we've taken the language model that knows something, and now we want to use RL to go even further. And indeed, we end up with a model that can learn to output the right pseudo eraser that can actually traverse in different environments based on observing that environment. So the whole idea here is that we get a proof of concept of going all the way from generating a data set to kind of using it in an RL setting. And the hope here is that this could also be more generally applied elsewhere. So the hope is to go beyond soda race. This is just our first proof of concept. There are lots of interesting other kind of code-based domains. Particularly interesting is like neural architecture search. Could you use this technology to kind of actually invent new neural architectures? Not just for Python. So although we use Python in this example, you can use other languages, HTML, Go, JavaScript, whatever has a lot of support in, say like a code script. Methodology is not dependent on this particular evolutionary algorithm, but can work with other ones as well. So we're really interested to see kind of where the follow-up work goes here. And I guess to conclude, one thing I think is really interesting here is that advances in language models may really enable new ways to embody or renew classical machine learning algorithms, like evolutionary algorithms. And so I think we live in an interesting time where we'll see a lot of interesting synergies and reinventions of the old becoming new again. So my contact information is at the bottom, and I'm really happy to take questions.